so this is section 13.3, day 2. And we've got basically 2 ideas we're going to try and do, kind of 3. The first thing is kind of the easier part, and this will pertain to 2 homework questions towards the end of the assignment, number 49 and number 50. And I said, what if I told you that there was a second quadrant angle with a sine of 2/5? Would you be able to figure out the other trig functions? And I would hope that yes, you can, because we've done this before in section 13.1. But now there's a new component, which is that I told you specifically it's in the second quadrant, which means that we move to the left and up to get there, and that stuff matters. So if we know that the sine of the angle is 2/5, it's a little bit inconvenient because those numbers don't play super nicely together, but that means that our side opposite is 2 and our hypotenuse is 5, because sine is the ratio of opposite over hypotenuse. If you know your side opposite and you know your hypotenuse, you know enough to know, well, some of the other trig functions and then to figure out the rest. So if you're given opposite, that's a leg. We don't know the adjacent leg, and we know hypotenuse is 5. The missing side is the square root then of 21. And that must be our adjacent side because we were told hypotenuse, we were told opposite. So we have square root of 21 for our adjacent side. The thing is, I have taught you before that when you apply a square root in a problem, you're supposed to do a plus or minus on your answer. And then we talked about how, well, if it's a triangle, it's a side length, so plus or minus doesn't make a lot of sense. It makes sense now because we care that it's in the second quadrant. To go to the second quadrant, you have to move to the left. If your adjacent side is how far you've moved, then you're going to need a negative number on your adjacent side. So again, hypotenuse we're assuming is positive, it always is going to be. And if you're in the second quadrant, then you move to the left and you moved up. This is a negative direction and this is a positive direction. When you think about how your angle theta is going to exist, or how your reference angle will exist, it's in there. That means that this is the side that is opposite, and this is the side that is the adjacent. Because the hypotenuse, of course, is across from the right angle. Take a second to absorb that, write it down. I'm going to erase it. Actually, I'm going to close the window and then I'm going to erase it. We don't really need the graph at all, actually, because what we've been asked to do is find the 6 trig functions, and we know that opposite is positive 2, adjacent is negative root 21, and hypotenuse is positive 5. And so the rest of it should be fairly straightforward because we're doing sine, cosine, tangent, and the reciprocal functions. So the sine was already given to us. It's 2/5. The cosine is not given to us, but we just figured out enough information to answer that. It's adjacent over hypotenuse. And the tangent was also not given to us. We were given side opposite, we're going to stick with it, but we figured out adjacent, and now we have our tangent. It's not nice notation, you're supposed to fix that stuff up. Square root of 21, top and bottom, gives you 2 root 21 over 21. There's a negative sign at the bottom, not so desirable either. On the side or on the top would be better. This is our gorgeous tangent. So we have sine, cosine, and tangent. If we want all 6 trig functions, it's no big deal at this point. We just have to flip the fractions. Some are easier to flip than others. Not an eventful flipping of the fraction. To do secant, though, we're going to have to flip this fraction, which again gives us radical in the denominator. It's annoying, but you can get through it. answer and flip it. But that would not be a good idea in this case because the fully reduced answer is going to have a radical in it. I'm better off actually flipping from here, negative root 21 over 2, because that needs no more attention from me at all. So let me get rid of this guy because it's just in our way. There. So again, the idea was consider that what you were given, and being told sine is 2/5, you were being told that your opposite is 2 and your hypotenuse is 5. And in being told that it's a second quadrant 2/5, then you know you're moving left and then up. All points over here are left and then up. They have negative x's and positive y's. And it's always going to be the case that your x-coordinate is your adjacent side and your y-coordinate is your opposite side. So it was no surprise to be told the sine was a positive value because hypotenuse will always be positive. Again, if it didn't make sense, try and let it sink in for a minute. Think about rewinding the video and watching again. And if after you've done that you still have questions, move on to example 2. And if that's done and you still have questions, write them down so you can ask about them in class. So this one we're going to do is a quadrant 3 cosecant negative 5 over 3. So cosecant of some angle theta is negative 5 over 3. The first thing you'll probably want to do with a question like that is translate cosecant for yourself. Again, every pair has one co, so cosecant already having the co sound doesn't go with the tempting option cosine, it goes with sine, which hopefully you're coming to already. So if it goes with sine, and we're being told that sine is negative 3/5. Sine is opposite over hypotenuse. The hypotenuse will never be negative. So this negative sign, it has to be a negative sign for the 3. It can't be the negative sign for the 5 because you'll never have that. So it's negative 3 over positive 5, which tells us that our opposite is negative 3 and our hypotenuse is positive 5. Again, we don't have to graph the whole thing out, but it matters that it's quadrant 3. 1, 2, 3. To get to quadrant 3, you go left and you go down. Both of those moves are negative moves. So our x will be negative and so will our y. That is, our adjacent side will be a negative number, just like our opposite side will be a negative number. So again, being quadrant 3, that's no surprise. Hypotenuse always going to be positive. We've got 2 sides, we can find a third because this is the basis of a right triangle. Opposite is a leg. When squared and added to the other leg, we'll get hypotenuse squared. And so that means that our missing side is plus or minus the square root of 16, which would be plus or minus 4. But it's not both, and it's not one or the other willy-nilly. It's, hey, it's quadrant 3. We're solving for an adjacent side. Adjacent sides in quadrant 3 are negative because to get to quadrant 3, you move left. So we actually know that our adjacent side has to be negative 4. This was a 3, 4, 5 triangle positioned in quadrant 3. So I'm going to get rid of the stuff that we don't really need. Taking up space. And we're going to do that. And then again, we can get back to what the question was, which is to find all 6 trig functions given that information. So we have sine and cosecant already done. And then we can get cosine, because we know adjacent is negative 4, hypotenuse is 5, we have cosine. The reciprocal for that is called secant. Again, negatives don't belong in the bottom. And if the fractions were not fully reduced, or if they had radicals, we have to deal with those things, but they're good. And then tangent is TOA, O over A. O over A. Best final answer for that doesn't have 2 negative signs. We'd let normal things happen in the fraction, divide a negative by a negative, we get a positive. The best expression for the tangent is that it's 3/4. The cotangent then, easiest way to talk about it is flip the reduced fraction, 4/3. Again, stop, rewind, rethink, write stuff down if you have questions. We'll be discussing, what we need to later. That's it of this idea. Homework problems 50 and 49 are just like that stuff. So the second big idea that we have is going to go back to two problems that we skipped in period 3 that we've dealt with in period 5 from section 13.1, and that's 27 and 28. So let's see. The shortest way to talk about this is that 30, 60, 90 triangles are special things. Across from your smallest angle is, of course, your smallest side. But what's special in a 30, 60, 90 is that across from your biggest side, you actually wind up, biggest angle, you actually wind up with a side that is exactly twice as big as your shortest side. If you do Pythagorean theorem, you'll see it play out that the middle side has to be a times the square root of 3. If a is the length of your side across from the 30, and the hypotenuse is exactly twice as big, then this is about 1.73 times as big. It's a times the square root of 3. What some people do is they actually say that they would like the hypotenuse to just be called 1. It's just convenient. If your hypotenuse is forced to be 1, then that means your a, the anchor in the problem, is a half. And then this gets written not usually as 1/2 times root of 3, but if you actually multiply it and put the 2 on the bottom, this is a standard way to represent the side. So across from the 30, we have a, or we have 1/2. Across from the 60, we have a root 3, or root 3 cut in half. And across from the 90, we either have 2a, twice the short side value, or we have a 1. 45, 45, 90 triangles are another kind of special triangle. What makes them special is that they're isosceles. Two equal angles means that the two sides across from them have to be equal to each other. And again, if you do the Pythagorean theorem on it, a squared plus a squared makes 2a squared. You take the square root of that, a comes out, 2 cannot, and you get that. So again, some people force the hypotenuse to be 1 because it's convenient in trig a lot of the time. That means that a would be 1 over the square root of 2, which folks don't like much because of slide rules. Long story, we've discussed it. So a, the building block of this triangle, you can either call it a, or you can call it root 2 over 2. Both of them are the same length as each other because they're across from an angle that's exactly the same opening. And so they're both a, or they're both root 2 over 2. So again, your hypotenuse, your two legs should both be a's, and that makes your hypotenuse a root 2. Or again, you can label it using numbers if you want to force your hypotenuse to be 1, which actually happens a lot. If that didn't make sense, go back through it. For 5th period, it should make some sense. For 3rd, it might be a little further out. But the purpose of those things is so that we can actually use the concept of reference angles and the labeling of the triangles using 30, 60, 90 special ratios to actually figure out random trig function values of angles that you think that you'd have to just go to a calculator for. You don't have to go to a calculator for this, and you probably won't even exactly know how, because that's a cotangent question, and you don't have a cotangent button. So, first move, draw the angle. 210 degrees is positive, so I'm going to open up. I'm going to go past 90 and past 180, but not that far past 180, because 210 isn't all that far past 180. How far past 180 is it? The reference angle is a 30-degree reference angle. It's 30 degrees past 180. So, I'm going to take a point from somewhere on the terminal side. I'm going to return to the x-axis, return to the origin, and lock in my little right triangle. We know it's a right triangle because we're going straight to the x-axis. And again, we know that it's a 30-degree angle inside our right triangle over there because we know that we have surpassed 180 by 30 degrees to wind up at 210. It matters a ton if that's 30. In all of these problems, your reference angle will be or 60 or 45 degrees. So the reason it matters is because we're going to use the ratios for these special triangles. And again, you can go with A root 3, 2a, or 1/1/2, and root 3 over 2. It doesn't matter. It'll shake out the same in the end. It does not matter. But what does matter a lot is that you're paying attention to where you are. So we have gone, to get to this point, we have gone to the left, which is a negative move, and then we've gone down, which is also a negative move. In quadrant 3, you're going to get negative, negative, as we've discussed. Negative, negative is adjacent, opposite. X, y is always adjacent, opposite. So across from the 30, I'm supposed to label either A or 1/2. I'm going to go with, I don't care. I'll do A's on this one and numbers on the other one. So this is across from the 30, slicing through the 30, I'm going to have my angle, my side length A. It's a negative A though, because that's a side that moved down. Across from the 90 is the hypotenuse. Hypotenuse will be either 2A or it'll be 1. I'm going to use A's for this problem, so I'm going to call it 2A. Hypotenuse is always positive. And then the remaining side must be the side across from the other angle. If that's 30, this has to be 60. So across from the 60 has to be A root 3 in this case, or root 3 over 2. But again, it was in the negative direction. To go from the origin to the point that's over here, we had to go left and down. The left is a negative x value. That's what this negative A root 3 is all about. The down is a negative y value. That's what the negative A is about. So, slicing through our 30-degreer, we can see that the thing that I labeled over here must be our side opposite. This guy is, of course, our hypotenuse, and this one must therefore be the adjacent side. Cotangent is the reciprocal for tangent. If tangent is TOA, that means that cotangent of 210 is going to have to come from the reciprocal, adjacent over opposite. So the cotangent of 210 degrees would be the side adjacent, which is negative A root 3, over the side opposite, negative A. It's a reducible fraction. The negatives cancel each other out, the A's cancel each other out, and we get this answer that you thought only a calculator might be able to provide. It's the square root of 3. 1.73-ish is the value of the cotangent of 210. If you want to check that out, you can go to a calculator and find the tangent of 210, and then just tell the calculator to take the reciprocal. You can raise it to the negative first power, or you can do 1 divided by the number. And it'll spit out the decimal equivalent of the square root of 3, which is roughly 1.73. Next item up for bid is the cosine of 405 degrees. So 405, let's see, that is more than 360. So we're going around the circle and then some. And then some by 45 degrees exactly. So if we were to sketch the angle, we would start in standard position, open upward, full 360, and then another 45 degrees, which lands us halfway through the first quadrant. First quadrant's a nice place to be because everybody's positive in the first quadrant. To get to a point over here, you'd have to move to the right, which is a positive move, and then you move up, which is also a positive move. First quadrant's positive, positive. So when we deal with adjacent, opposite, it'll be positive, positive. Our x, y at that point is positive, positive. So again, it really matters that we had a 405-degree angle, and that our nearest location of the x-axis would be considered 360. I actually already calculated the reference angle because I needed to place the graph properly. That then is a 45-degree angle. Given a 45-degree angle, we're dealing with a 45, 45, 90. That's A equal sides across from equal angles. A root 2, what you get if you do the Pythagorean theorem on those guys. We can also say this is root 2 over 2, or root 2 over 2, and 1. Doesn't really matter really make a difference. It won't matter ultimately. So I'm going to go with numbers on this one because I did variables on that one. So I'm going to go with these guys. Across from each of the A's, so each of the 45 degrees, I'm going to write a root 2 over 2. Across from the other 45 degree, we've got a root 2 over 2. Our right angle is right here. Across from it is the hypotenuse, which we're calling 1. If this is where theta is, which it is, theta is always at the origin inside the triangle you just drew. Slicing through it, we have our side we call opposite. Slicing through your 90, we have the side we call hypotenuse. And then the last side is our adjacent side. This question was to find the cosine of 405 degrees. Cosine is chi, A over h, adjacent over hypotenuse. Our adjacent side is root 2 over 2, and our hypotenuse is 1. Anything divided by 1 is just itself, so our final answer is just root 2 over 2. Square root of 2 is about 1.4, square root of 2 cut in half is about 0.7. If you go to a calculator and you ask it and you're in degrees mode, what's the cosine of 405 degrees, it should spit out 0.707 because that is what it is. Hope you're doing okay with this. When it comes to the stuff that's in radians, you really probably should switch it into degrees first, then draw your sketch, then do the reference angles. I'm not going to do the whole thing because I can't imagine you're going to watch the whole thing and I'm getting really tired. It's actually 7:50 on Friday afternoon. I'm still at school. So, 5 pi over 6 is a radian measure. It's almost 6 over 6, so it's almost 1 whole pi, but it isn't quite. So I have to use a tool from section 13.2 to convert this into degrees so that it's manageable for the rest of the problem. I don't expect you to memorize 30, 60, 90s or 40 or 45 90s in radians, so we have to convert this into degrees. If you want to kick out pi radians and introduce degrees, you're going to put your form of 1 with degrees on top and your pi radians on the bottom. In multiplying across, you get 5 pi 180 degrees over 6 pi. You can obviously cancel your pi radians, that was your purpose. And then it turns out you can also cancel 6, it reduces with 180 degrees by 30. So all that's left standing is that 5 times 30 degrees, this is a 150 degree angle. Which again should make some sense with the estimate I gave before. That's almost 1 full pi, that's almost 1 straight line, 150 degrees. Those angle measurements are totally commensurate, so the sine of 5 pi over 6, if you're in radian mode in your calculator, will be exactly the same as the sine that we're going to calculate of 150 degrees if you're in degree mode in your calculator. So again, you care about what your reference angle is, return to the x-axis, return to the origin, lock in the right triangle, that's where the right angle is. This guy here is the angle that we're really interested in. It's our reference angle. And it's the difference between stopping at 150 and going all the way to 180. Again, don't be surprised. Every value you get is going to be a 30, a 60, or a 45 degree. Other essential ideas to think about is that to get to this point, we have to go to the left, and then we have to move up. Then again, you go back to your 30, 60, 90 ratios, fill in across from the 30, across from the 60, and across from the 90. Remember that sine is so, and simplify. We'll do the same thing for this. I just feel like we're probably both running out of patience for me doing examples. It'll be better when you just start trying it yourself. So the last bit is kind of an extension on that idea. Because as you may think about, not everything can have a right triangle drawn for it. A quadrantal angle is an angle that hits where the quadrants are marked. So at 0, at 90, at 180, 270, 360, and actually any multiple of 90. They also exist in radians at 0, at pi over 2, and pi, and 3 pi over 2, and 2 pi, any multiple of half You can't draw a triangle for those, so we need another way to figure out what to have to do with them for their sines and cosines and tangents. Something you probably noticed me doing a bunch in the last few examples was looking at things and going x comma y and also labeling them with adjacent comma opposite. X comma y was negative, negative. That also translated to adjacent comma opposite. Fortunately for us, this is one of those things that, like x and y, is alphabetical. Adjacent comes before opposite, and this will always be true. And so basically, something that you can think about is that, so if you know a point, then you can just use Pythagorean theorem and consider the points x and y, adjacent and opposite, those are the legs. Use Pythagorean theorem to get the hypotenuse. You may or may not be given a point, but if you are, this is one way to handle it. Your book phrases it like this. I'm not a fan, this isn't how I think. I don't memorize formulas successfully. I have to kind of like just try and understand this stuff and reproduce it myself. But if you're interested, this is how your book talks about it. Again, not my favorite thing. But what you can do is draw in, like you can't draw in the triangle, so you can basically just imagine that if we've got 5, 0, there's no triangle I can draw, but I can interpret that as adjacent comma opposite. And then I can calculate the Pythagorean theorem, a squared plus b squared equals c squared. And I can find the hypotenuse that way. So 25 plus 0 is, of course, 25. And hypotenuse, therefore, would then be 5. Because you apply square root, you're supposed to do a plus or minus, but not hypotenuse. It's always positive. So then what we are coming to is that hypotenuse must be 5, just like adjacent. And so now you have opposite, adjacent, and hypotenuse, and you can find any trig function you want to. So the 6 trig functions for this guy, sine, cosine, tangent, to start off with are opposite over hypotenuse, reducible to 0, adjacent over hypotenuse, reducible to 1, opposite over adjacent for TOA, reducible to 0. So the sine of this angle is 0 and its cosine is 1 and its tangent is 0. If you want to do the reciprocals, you sort of can. Cosecant is actually undefined because it'd be 5 over 0. Can't do it. Secant, no problem. The reciprocal of 5 over 5 is still 1, or the reciprocal of 1 is still 1. And cotangent also what? Yeah, undefined. You flip that fraction, you got something over 0. You can't do it. It's undefined. So if you have a quadrantal angle, an angle that hits on a quadrant marker, if it's labeled with a point, it's easy because you can think of it as adjacent comma opposite and use that to calculate the hypotenuse. And now you've got all the building blocks you need to figure out your 6 trig functions. If, though, you were just told, hey, find the 6 trig functions of a 0-degree angle, you need to realize that a 0-degree angle is in exactly the same spot as an angle that happens to have the point 50 on it. Does that make sense? The point 50 was here. The angle that describes, if its terminal side is where its initial side was, is a 0-degree angle. So I could have asked the exact same question and called it a 0-degree angle. And now you know the sine of 0 degrees, the cosine of 0 degrees, and the tangent of 0 degrees, because you just figured them out. 0, 1, and 0. And again, pick up a calculator if you want to and ask it in degrees or radians, what's the sine of 0? It'll tell you 0. What's the cosine of 0? It'll tell you 1. What's the tangent of 0? It'll tell you 0. So what we do is, if we have a quadrantal angle, basically, if we have a quadrantal angle, what we do is we imagine a point that it's sitting on. So like, I said less than this here, wishful thinking. If you have like 270 degree angle, then what you can do, and it seems like a weird thing to do, but you can say, look, there's an infinite number of points on here, I'm going to select one. That point somewhere on the y-axis has to have an x-coordinate of 0. And then it has some value for a y-coordinate. I'm going to say, whatever, y. I'm feeling very creative at 8 o'clock at night. So this is over 0 and down y. It's apparently a negative number because of the position that it's in over here. So opposite and adjacent are embedded in here. It's adjacent, opposite. Because the order is alphabetical. It just works when you're drawing an actual triangle, and it extends to when you can't draw a physical triangle. So if we were asked to find, let's say, the tangent of 270 degrees in particular, hopefully I'm not answering an exact homework question by accident, but we can just make up some random point that's over here. And I mean, you can use an actual number if you're more comfortable. Let's call that 0, -5. Maybe that'll be easier on you. We went over 0 and then I arbitrarily went down to 5. I could have gone down to anything, but this has to be over 0, down something negative. So adjacent opposite, when squared and summed together, will give us hypotenuse. Oh, silly me, you don't even need hypotenuse. Tangent is opposite over adjacent. So this answer, done before I realized it was going to be undefined, can't do it. But you can answer the question, even though the answer is undefined, it's still answerable by realizing that you've got your adjacent and you've got your side opposite, and tangent is toe up O over A. If I had asked for like the sine or something, then we have to go through this process and figure out the hypotenuse is, of course, 5 again. Because no matter the direction we went in, hypotenuse should always be a positive. And so if we were asked, A, what's the sine of 270 degrees, we'd say opposite, -5, over hypotenuse, +5, and we get -1. Again, it's the kind of thing you can confirm in a calculator should you wish to. But it's 8 o'clock and I'm going to go. I hope you've had a good Memorial Day weekend. I'm going to start mine. And I'll see you guys Tuesday. And this video is